Okay, so today I'm going to talk about rasterization. So we're basically going to kind of close the OpenGL pipeline, so to speak. So if we start on this side of the board by drawing up this age-old image here, vertex shader, got clipping, which we have looked at. In the vertex shader, obviously, we have geometrical transformations that we've looked at, model matrix, view matrix, projection matrix. We have light calculations here as well. Although sometimes we just prepare the light calculations here and then do more in the fragment shader. Clipping, window to viewport, transformations. And in the end here after this, after we've kind of rasterization. At this point, when we've kind of gone from our general three-dimensional model into a continuous two-dimensional model that we clip against, window to viewport takes these two-dimensional vertex positions actually to the screen, to the actual locations on the screen that we're going to be drawing into. What rasterization does is, if we imagine at this point we have the positions in the viewport here. So we have the vertices. We even have some data that's linked to these vertices. We have their positions. What rasterization does is it takes these vertices, these vertex locations on the screens, and it fills them in. So that's the base functionality of rasterization. Is basically finding all the actual pixels that will be affected by this particular polygon that we're drawing, and actually putting a color in the frame buffer to those particular pixels. And once we've kind of put this into the frame buffer, we have our actual physical computer screen reading from this frame buffer and reading this data onto the screen on the correct pixels. So that's what rasterization does. So up until now, we've been working with vertices. We have vertex data that is mainly the position, but we also have these directions, the normals for each vertex that we use for the lighting calculations and so on and so forth. In the end, we find a color for the pixels here in the corners, or the pixels in the vertices of this polygon. And the rasterization not only fills this in, although that is the first thing that it does, it actually fills all of these in with the correct color. And if these are different colors, then we need some policy to decide what's the color of a pixel somewhere here in this polygon that's not on the vertex. So we have the colors for the vertices. So rasterization kind of has a policy of how do I fill in the color for the rest of the pixels that this polygon fills in. And then we look kind of further into this and say, what if we just don't have only a color here? What if we actually have other data? Like we've been doing per fragment lighting, where we do the lighting calculations for each pixel. Then instead of having a color here, we have normals or directions and things that we need for the lighting calculations. But again, each of these vertices has that data, has data for the varying variables in our shaders. And the rasterization needs a policy to take the values for the corners, interpolate them onto all the pixels here, and then somehow do this calculation for every pixel. So that's what we're going to be looking at now, the rasterization. Inside the rasterization, we have our fragment shader, and our fragment shader is basically the shader calculation or the whatever color calculation that is called for every single pixel in our system. Any questions regarding this idea, this just base idea of the rasterization? So there are a few definitions that we're going to go through as we go along. But yeah. Can anyone see if they were tasked with writing this algorithm? You're just told, okay, let's keep it simple now. In a two-dimensional viewport here, in a two-dimensional grid, you are given the XY coordinates for 3 points here. And firstly, what I want you to do is to fill in with a color. Let's just say it's black and white. It's just 0 or 1. I want you to fill in with a color value all of the pixels in this grid that will be part of this polygon drawn between these points. That's kind of our base here. So let's go ahead to the other side. Stronger color than that. So let's just imagine we have this here. We have, let's just call these points P1, P2, and P3. And let's just start with a very specific case, just exactly these positions for P1, P2, and P3. You can see that in some cases P2 and P3 might both be to the right side of P1. P1 doesn't necessarily have to be at the bottom, so on and so forth. But just for this case, what I want to do, I know that there's a pixel here. Let's just imagine that we have already discretized these values here. So these are integer values and they just represent an actual absolute single pixel, each of them. Now I want to fill in every single pixel that kind of touches this form. Where would I start?
P1.
Okay, start at P1. So what kind of programming method am I going to use to do this? Something simple, go back to programming 1. What are we going to make?
List. For the list, right?
Do we need a list? Let's just say I don't need to actually store these. I just need to set their values. I have access to this data, which is the frame buffer. Frame buffer. And I can access it in this way. I can say frame buffer number x, y equals some color. This is something that I can do. And I know the xy coordinates of P1, P2, and P3. So I can use P1x, P1y, P2x, P2y, P3x, and P3y. So I'm going to repeat something for every single one of these pixels. So very basic programming method of repeating something. No, loop, thank you, a loop. We're going to do a loop. The question is, where are we going to start this loop? So let's just set up a for loop here. This is going to be my outermost loop. I'm probably going to have to rewrite this a lot of times because I'm going to have to fill in more stuff. But for now, let's just set up a loop that kind of gets to all of these locations. And we want this loop not to kind of go through the entire screen, and then if something is inside here, I draw it, otherwise I don't. I want to make a loop that actually only iterates over the pixels that are actually part of this. Does that make sense? So instead of looping over the entire screen and checking, is this pixel within this polygon or not, I'm going to say my calculations happen before I even loop. I want to only iterate over the pixels that are actually there. All right, so now the question is, if I start at P1, like my outer loop, is it going to go where? If my first iteration is here, where's my next iteration?
P2.
Is it? Because I'm kind of thinking, this is my screen. I have this grid here, and I kind of need to fill in all of this. So I'm in some way, yes, I'm going towards P2, but if I start at P1, I'm kind of starting at a specific y value, right? And I want to go up to some other y value. I want to start here, and I want to go up to here. Starting at y bottom, ending at y top. Does that make sense? So I'm going to call each of these iterations a scan line. So here I have some y, just random y going from here to here. I'm at some point. Then this here is kind of my scan line. For each y value, I want to scan from some x left to some x right, and I want to fill in the pixels along this. Then I want to go up to another y, and then I want to scan here, fill that in, go up to another one, fill in, so on and so forth. So I'm filling this in like so. Does that make sense as an algorithm to fill in all the pixels here? So I'm going to say for some y, which starts at, I'm not writing this in Python code, doesn't matter which kind of pseudocode I do here, starting at, let's just say y bottom, and it's less than or equal to y top. So I'm going to begin at y bottom, I'm going to end at y top. Okay, this is kind of a C style for loop, except this. Or we can go ahead and do it Python style here. For y in range, y bottom, y top, I'm going to do the following. Okay, so what this for loop is going to do, if nothing else, it's going to go from each value, basically make a y value for each value from p1y up to p3y in this particular image. But again, we can see that if these were labeled differently, this might go from p2y to p3y or from p3y to p1y. Doesn't matter. We go from the bottom and we go up to the top. You can later think about algorithms to decide which point is at the bottom, which point is at the top, which one is right, which one is left. Now let's look at this particular scan line. I want to find the leftmost pixel in this with this value of y. And I want to find the rightmost pixel, x right. Is there a nice way to calculate this?
Yes.
Yes, there is. I'm gonna go ahead and throw in a little definition here. Just make it small. I'm gonna limit myself to this space here. Linear. Let's stick to all caps since I started that. Interpolation. Yes, I did spell that right. Linear interpolation, which is, I'm going to call it the function lerp. So I'm going to linearly interpolate between two values. A linear interpolation can be between anything. It can be a linear interpolation between two vectors, a linear interpolation between two floating point values or two integers or whatever. But I'm going to say I have a value A, I have a value B, and then I have kind of a ratio or a parameter. So I have A, B, and I have a parameter T. And we can look at this like a linear function. We've already looked at things like I have a point A here, I have a point B. And if we have a linear interpolation between these, we kind of have a line. So we looked at the parametric form of a line, where we actually took a point and a vector, and we said, somewhere on this line, I have the point A plus T times the vector between them. So I could say P equals A plus T times B minus A. Yeah, basically that, A plus T times B minus A. I can also mix this around and say this can also be 1 minus T times A, because here I have 1 times A, and here I have minus A times T. That's 1 minus T times A plus T times B. If I take the parameter T and I put a 0 into it, I will get the point A. So T equals 0 gives me the first point. T equals 1 gives me exactly the second point. You can see here 1 minus T gives me 1 times A. If T is 0, that's 1 times A, and 0 times B. If T is 1, I have 1 minus 1 here, which is no A, plus 1 times B, so that's exactly B. Everything in between, from 0 to 1, gives me some point along this line, P. Values lower than 0 will give me something here. Values higher than 1 give me something here. Okay, so I have a definition for a line in this case, but also for a line segment that starts in A and ends in B, if I make sure the parameter is between 0 and 1. This is similar to what we've used in kind of deciding if a collision happened, in the past or in the future or within this frame. Just decide if the parameter is between 0 and 1 or between 0 and delta time, it's within this range that we're looking at, otherwise it isn't. However, this is kind of a special case. General case of linear interpolation. The linear interpolation of two things and some parameter t is 1 minus t times the first thing, the first object, plus t times the second object. So I'm linearly interpolating these things. If I have 0, I have A. If I have 1, I have B. Anywhere in between, I have a weighted average. So this is a kind of weighted average. Weighted average between 2 points. Now, when I'm going to use linear interpolation, I have to decide firstly what is A and what is B, and then I need to decide how do I calculate the parameter t so that it makes sense, so that it takes the correct weighted average between these two things. Now, if we go back to the other side here, what we want to do in some random pixel here is we want to say I have color values for P1 and P2 and P3. In this particular pixel, I want some kind of a weighted average of those color values, right? Very close to P3, I want almost the color that's on P3. And when I'm drawing P3, I want exactly that color. As I go into the other pixels here, I want to get closer to the value of P2, closer to the value of P1, without there becoming sudden lines or shifts in the color of this. I just want it to gradiently go from this color smoothly over the entire polygon to the other colors in the corners, so it looks smooth. So these weighted averages and linear interpolations are something that we're interested in. So now back to this. Let's start with our first linear interpolation. We want to use linear interpolation to find x left and x right. And again, let's allow ourselves to just look at this special case, not the general case, where P1 is exactly here, P2 is a little bit to the right, and P3 is at the top and a little bit to the left. So how can I find x left here? I know the y values. Like, what could my parameter be? I want somehow to mix some values of P1 and P2. What do I know? Like when I'm here, I'm pretty close to P1, I'm pretty far away from P2. So I probably have a weight or parent parameter that's close to the y value of P1, right? Or close to 0 in this case. As I go up here, I'm getting closer to P2. And my parameter should probably be getting closer to 1. So can I somehow build this? Can I use the y value of P1, P1y, the y value of P2, and the y value, which I know, because the y value, general y value is part of my loop here, can I use those to basically set up a parameter that goes from 0 when I'm here to 1 when I'm here? I can, yes. Can you tell me how?
1 minus the distance for P2, distance for P1.
Okay, distance from where to where?
From P1y to the y you're scanning.
Okay, so that would be y minus P1y, right? Or let's, oh, there was an eraser there. Move it a little bit inside here and say, we're looking for x left. All right, so we're going to say y, which is the y value we're scanning, minus P1 dot y, right? So that's this distance. So the ratio of what do we want?
The ratio of P2y, no, 1 minus P2y.
Or P2y minus P1y. Like we're taking this distance here divided by this distance.
Oh.
And we get a percentage or a range from 0 to 1.
Oh, yeah.
Prósenta er jafnt á hluti deilt með heild.
Yeah.
We heard that in grammar school. Fair enough. So our ratio is the part divided by the whole. So this is going to be P2y minus P1y. Again, this works when the points are arranged in exactly this way. Let's just stick to that for now, but you understand if suddenly this one is labeled P3, then we have to switch that out here as well. Or is this x left? No, this is just my ratio. So what is x left? So I'm going to say here, I'm going to call this t left. What is x left?
Would it be linear interpolation of P1?
Linear interpolation, yes, of P1.
Y?
No, is it?
Is it the other way around?
So I'm using the y values to decide the ratio because I know how far along I am from P1y to P2y. But it's the x value that's the unknown. So I'm going to say if I take the linear interpolation of the x value of P1 and the x value of P2 and the ratio that I know in the other dimension, I'm basically taking the ratio in this dimension and moving it into this dimension. So the linear interpolation of P1x and P2x and with the parameter t left, or the parameter y minus P1y divided by P2y. All right. Can I do the same for x right? What would my t right be then? Very similar. Y minus P1y divided by, in this case, I can see that the right side is between P1 and P3. So we can also see that the right side is always going to be a ratio between P1 and P3, whereas the left side is going to be from P1 to P2 until we're here. If I were taking a scan line up here, it would be between P2 and P3. So we'd simply have to incorporate that into our algorithm. It's not just one loop, it kind of has to be two loops. One that goes from the bottom to the middle point, another that goes from the middle point to the top. But for now, let's stick to this. So t right, y minus P1y divided by P3y then, minus P1y. And x right equals the linear interpolation of P1x, P3x, because in this case this is a line that we're going along, that's from P1 to P3, and this t right parameter. Okay, so we found x left and x right. What do we want to do now? So we want to fill all the pixels along this scan line in, right? So what do I need to do to repeat several iterations along this? Another loop, cool. So for x now in range x left to x right. Actually, this is not correct Python code for this because we have to make sure we're actually going to y top. So maybe y top plus 1. So we actually have to include y top in this, and we have to include x right in this. We have to go all the way to x right. What do we do here? If the only thing I wanted to do is to simply fill in some color for every pixel that is there. Can I just take this line and say frame buffer number x, which I get from this loop, y, which I get from this loop, equals just whatever I want it to equal. Let's imagine we had a black background and I want a white color. Something like that. Again, pseudocode. So we just take some color value and we put it into the frame buffer at x and y. So at this point, we filled everything in, right? Yeah, until I reach P2 here, then we'd have to switch this. So yes, in reality, we'd have to kind of check, okay, which point is at the bottom, what do I label that? What I would do probably is to say I have these 3 points here. I'm going to find the bottom one, and I'm just going to relabel that P1. I'm going to find the top one, and I'm going to relabel that P3. And the only thing I need to do is to figure out if P2 is to the right of the line between P1 and P3. So it's x left that will switch somewhere along the middle, or if it's to the right of it, so that it's x right that will switch. After I know these things, I can do one of 2 sets of for loops. Either one that goes from P1y to P2y, doing a linear interpolation between P1 and P2 values on the left and P1 and P3 values on the right. Then I'll do another for loop that goes from P2y to P3y, doing linear interpolations between P2 and P3 on the left, still P1 and P3 on the right. Or I'll do the other set, which does P1 to P3 on the left, and P1, P2 first, and then P2, P3 on the right. Does this make sense? But in our case, we're mainly going to understand how this works. If you get examples, you can draw them up and just look at it and see which ones fit. We're not going to program this ourselves. This is one of the things that we are happy to have OpenGL do for us, and not dive too much into exactly what we'd have to do to get this fully optimized. But still, we want to understand how this works. Now my question is, what if I'm not content with this? What if, and let's change colors here. What if P1 did not only have x, y values here, and P2 and P3 as well, but it also has a red, green, blue color value. Let's imagine in this case that we did our lighting calculations in the vertex shader. So we did the lighting calculations here and we ended up with a full color. So we end up with some color here. And I don't know how many of you noticed, but in the first shader that we didn't really start editing, we just had one varying variable and it was called v_color. And that's basically simulating what the static pipeline used to do, which is it just had its one built-in color. And after its kind of lighting calculations in the I coordinates here, which are now done in the vertex shader, it would set that color, and that color would be linked to the vertex as it went on through the pipeline. We do the same thing here. We take a color and we link it to the vertex. So let's say we just take the color, hang it on here, we do the lighting calculations per vertex, no fragment operations. Get back to rasterization here, and every single pixel, so each of these 3 pixels here, has XY coordinates in the viewport, and it also has this color linked to it. Now my question is, how can I change this code here in order to simulate that? That I got a color for each of these, but for some pixel here, I don't just want one of those colors. That's what the static pipeline originally called flat shading. Then the first vertex that came in had a color, and that color was simply set to all of the pixels that were here. There was no shading. There was just, you got a color for one of the pixels, for one of the vertices. The other vertices were simply sent through geometrically, and then the color for the first vertex that was calculated using lighting calculations in I-coordinates was simply flatly shaded over the entire thing. So it was just one color for the entire polygon, flatly shaded over. Or you could set another switch which asked for smooth shading, but smooth shading was still not fragment lighting or pixel lighting. Instead, that was still vertex lighting. We got smooth shading, which meant that for every pixel here, it got a color that was some weighted average of the other colors. So that when we rendered an entire object, we get this smooth transition of color over the object, rather than kind of flat sections of color. Again, to my question. I'm just babbling here. My question is still, how can I get this effect? What can I do here? I've linear interpolated x left and x right. Now I have x left and x right. I have color values for the pixels. How can I use linear interpolation now to get color for this? Change this line here and say the frame buffer number x, y equals some actual calculated color here.
It's like ratios that add up to 1 for all the points, so you have to apply the color values.
Okay, ratios that add up to 1. I don't necessarily need to calculate a weighted average between all three of these values when I'm in this pixel. Maybe it might be nicer to kind of have intermediate values and do simple linear interpolations here. Like, let's imagine that I'm going to do a simple linear interpolation here and say this color is now a linear interpolation between what color? Some color left, maybe? Some color right? And some ratio here between x left and x right. But in order to get that, I probably needed to calculate intermediate color values for left and for right. And I can fairly simply calculate those using probably the same ratio as I used to calculate the x value. Does that make sense? Could I go ahead here and say the color left equals the linear interpolation between P1, let's just call it P1.c, the color that's linked to the point P1 or the vertex P1, P2c, and T left. So we're using the same ratio here as here, this ratio here, y minus P1y divided by P2y minus P1y. I'm going to say the color for the right pixel, color here. So I've got an x value, a right x value, and now I've linked a color value to that. I've got a, left value. I've got a x left value, and I'm going to link a color value to that. Left, right, yes, I'm not mixing that up. Linear interpolation between P1 color, P3 color, and T right. Now I'm going to do my x for loop here. For x, just to say from x left to including x right. Do this. Change this up here as well. For y, from y bottom to and including y top. So now the final question is, before we take a short break, What's the ratio? Well, we have some x here, right? So we have an x. We're taking an x from x left to x right. So we want this to be 0 in the beginning, right? So when x is x left, x minus x left is 0, divided by x right minus x left, 0. When we're in x right, x minus x left is the same as x right minus x left. So x minus x left divided by x right minus x left gives us 1 when x is x right. So x minus x left, the part divided by the whole, x right. So basically, how far along are we from x left to x right? And what is the total distance from x left to x right? So the total distance is x right minus x left. How far along we are is x minus x left, which is 0 when x is x left. And this whole thing is 1 when x right, or x is x right, because then we have the same thing falling below. So that's going to be our linear interpolation. So what we have here is called, and I don't know if this, I'm probably spelling this wrong, Golrod shading. And remember if the U on which side of the R the U is. Can someone search that? Is it Golrod or Golrod shading? And see if it actually shows. Yeah. So this is simply a name of this type of shading where we calculate a color for the vertex, and then our shading is simply linearly interpolating this color over the scan lines for the x left and x right values, and then linearly interpolating the left and right values over the pixels. So this is going to give us kind of a gradient here. This is going to give us the effect that we get when we have per vertex lighting and smooth shading. Do you find Golrod shading somewhere?
Yeah, it's Gourau.
Thank you for the spelling. Golrod shading, as opposed to what's called Phong shading, which is what we get when we actually move the lighting calculations, or half of the lighting calculations, into the fragment shader. Let's take a short break before we look at that and more things here. But what we have here now is basically our skeleton, or our base for the rasterization algorithm. It just goes from the bottom to the top. It takes one line at a time. For each line, it finds a left value and a right value, and it walks every pixel between those values. And for each pixel, it calculates a color. And that color is calculated, in this simple case, by simply taking a linear interpolation between the color values that are stuck on each of these vertices. So after the break, we're going to look at how we incorporate the actual fragment shader into this, and where that fits into this algorithm. Já. Jú, ég ætla að setja tölvunni í samband svo slökkur ekki á sig hérna í mér. Kafi. Já, ég sé þetta var. Ég nokkuð viss að tölva myndaði við það sem ég fer yfir. En ef þú gerir þessa breytingu og hendir verðinu aftur, þá má það.
Þú veist, þetta er einu.
Já, ok.
Eitthvað ekki hentum komment eftir.
Jú, getur hendin kommenti, gerðu það bara. Þessi komment fara stundum fram hjá mér samt í yfirferðina þegar það byrst sitt á hvaða mismunandi stöðum í Canvas. Því miður eru assigned comment ekki frábær leið til að eiga samskipti við kennarann. En jú, hendin kommenti, ég var með eitthvað svipað daginn og ég testaði það á tölvunni minni, allavega á fartölvunni og þá keyrði það hvort sem það var 0 eða 0,0. En það er dálítið mikilvægt að passa upp á þetta því að shading languageið sem við forðum shaderinn okkar í, það er strongly typed, þannig að það getur raunverulega litið sem svo að það stendur ekki 0,0 og þá sé þetta integer, þá sé þetta bara ég er ekki með neitt fallið sem tekur integer þarna, þetta verður floating point.
Compiler á sama systemi heima.
Já, það er bara önnur tölva. Það er hardwareið sem hefur áhrif á hvort það compilast eða ekki. Nei, þannig að þá er það. Já, ok, þannig að þetta er bara keyrið á.
Hvað á annars að vera í skýrslunni?
Bara alls konar. Bara það sem þú vilt. Það er náttúrulega lýsing á því sem á að vera shaderana í því verkefni. En það sem er ágætt að bæta inn er bara svona smá general lýsing á leiknum, eða þú veist, á forritinu ykkar. Og hvort ef þið gerðu eitthvað sérstakt að það, ef þið gerðu eitthvað method sem ykkur finnst áhugavert og ykkur finnst að eigi að hafa einhver áhrif og ég eigi að taka eftir, endilega skrifið það þar. Þið er meir líkur á að taka eftir því ef þið explicitly segjum frá því, heldur en ef ég á bara að fatta það. En heilt yfir þá snýst þetta shaderana, að þið farið í gegnum shaderana bara línu fyrir línu, ekki shader klasan í Python, þetta shaderana ykkar og segja hvað þessar línu gera. Þetta er bara leið fyrir mig að sjá að þið skiljið hvað setningar ykkar. Ég kópir það bara inn í skýrsluna. Ef kommentin eru nógu detailið til þess að það finnist það, en ég ímynda mér að komment þurfa að vera heldur detailið til það sem ég er að byrja. Ég vil fá alveg smá skilning á útreikningum sem eru að gerast ef þið eru að senda hluti á milli vertex og fragment shader þess að útskýra þetta er það sem gerist, svo on and so forth. Þá pínu smá útskýringar á því hvað hver lína gerir og hvaða ljósauðdrykkanir eru og diffuse og spekular og eitthvað. Þetta er svona aðalega það. En skýrslan verður að innihalda þetta shaderana og útskýringu á ljósauðdrykkanum. En svo er optional að bæta inn bara general lýsingu á því sem þið gerðu í leiknum til að hjálpa mér að fara yfir.
Þetta sé ekki að þetta kemur í
Ég ætla að fara að fá mér vatn.
Gott. Skil. Ég veit ekki hvað var með svona bólflög eitthvað með, en það var sneðar veist. Þetta var stórfækjum.
Okay. Let us switch for a moment. Over to this screen here, or over to this board. And let's kind of fill in very short pseudocode here in the rasterization for what we were doing earlier. Just basically for y bot or y in y bottom to y top. We're going to do something. In that case, we find we find x left and x right. We find x left and x right in here. In our case there, we said we find color left and color right as well. Then we have another for loop here for x in x left to x right. We do some stuff, and within that we basically said the frame buffer number xy equals some color here. And this color we calculated last time around. We said color is the linear interpolation between the color left and the color right, and some ratio here, x minus x left divided by x right minus x left. So this is kind of an overview over this algorithm. For y, we do each scan line. So each iteration of the outer loop we call a scan line. Each iteration of the inner loop is a single pixel or a single fragment. So the fragment shader itself, it has all of these varying variables. Like originally we just had v color. So if we go back to that and say, okay, we have main here, and what main did was the only thing that it did was it said GL frag color equals v underscore color. So the first time we looked at this, it was really weird because in the vertex shader we just said v color equals something. Then in the fragment shader suddenly we say GL frag color equals v underscore color. And it seemed like we were just setting this value twice. Like we could have just set GL frag color to v color at the beginning. But the thing that happens in between here is that it's not only the colors, it's not only the single color that gets linearly interpolated, but instead, I'm going to take this out and say, in the general case, here we're going to find left and right values for every varying variable, for every varying variable in our shader program. Can you read this here? Okay, I hope it can be read on the video as well. So for every varying variable that basically was set in the vertex shader, so every single vertex now has a variable kind of hanging onto it, a chain of variables. And what we basically the place we decide how many variables these are and what they are is the varying variables that we define in the vertex shader. We set values to them, those values get linked to this vertex, and those values continue on through the entire pipeline until we're in rasterization. And then we go in here and we say, okay, for every single one of these varying variables that we defined in the vertex shader, and we defined in the fragment shader as well, we are now going to linearly interpolate left and right values for all of them, based on the values in the vertices. Then we go into our inner loop here, and then we say, find fragment value for every varying. So for every single varying variable that we found left and right values for, we now find the actual fragment value for this particular pixel. Then add a color here in. We set values and run the fragment shader. We basically set the values to these varying variables, the values that we find here, and then we run the main function. Run the main function of our fragment shader. Does this make sense? The fragment shader, at some point, I'm going to write this here, the fragment shader does some stuff, and then it says gl underscore frag color equals something. In our first case, it just equaled v underscore color, but it wasn't the same value for v underscore color as the one we set in the vertex shader. It was a linearly interpolated value of all of those values for this particular pixel. So in the fragment shader, we simply took that value. The calculations had been done for us. Rasterization did the calculations of the varying color for us. We just set it to frag color here, which still meant that we were getting different values for frag color in every single pixel. Even though we were using the same variable, this variable had a new value every time. Because for every pixel, the rasterization will calculate a new value for each of the varying variables using linear interpolation. And so we set GL frag color to something. So GL frag color is the main output variable from the fragment shader. And now OpenGL has access, after it's run the fragment shader, and the fragment shader has finished its run, OpenGL now has access to GL frag color, which is what it actually sets in the frame buffer. So at this point we say, let's make a little more room here. We say the frame buffer, the actual value in this pixel, x, y, in the frame buffer that the screen then ends up reading from, equals GL frag color. Are there questions regarding this? To me, this makes complete sense, but when I look at the board, it's just a jumble of letters and stuff. So I'm not sure what you're seeing here. The clarity and perfection of the rasterization algorithm that I see, or just a jumble of letters. You can raise your hand either way. However, there's a lot of things that we've left out here. The only thing that happens here is that we kind of fill in. If we go to the other side of the board here, we fill in all the pixels that are here. Once we then draw another polygon, if some of the same pixels are in it, if it overlaps, it just puts that second polygon right over, and everything is just rendered in the order that we render it. We have no way to decide if something's in front or something's behind. We have no way of having some things semi-transparent or stuff like that. This base rasterization that we have here just takes color and puts it in the frame buffer. However, all of these things, the depth test, alpha blending, transparency, all of those things, they happen inside our rasterization algorithm. They are fragment operations. Some of them happen inside our fragment shader. So some of them we do ourselves inside the fragment shader. Some fragment operations we make ourselves, we program them ourselves inside the fragment shader. Some of them happen in OpenGL's rasterization either before or after we run the fragment shader. Like blending actually happens, we can make that happen after we run the fragment shader. We just have to set particular switches in OpenGL and tell it how it's supposed to blend and what values it's supposed to use. I'm not going to go into blending here, but just remind you that it happens in here. We'll go into blending next week or the week after, depending on where we're at. But we will look at blending and we'll use it and we'll see how we can do transparent objects. We'll see how we can do objects that kind of accumulate color so we can get energy effects and things like that. Like not only semi-transparent things like colored glass, but also energy effects like fire and electricity and things like that. Things that kind of, accumulate color in particle effects, explosion particle effects, things like that. These things that are kind of these effects, this blending of color, making the color not just be these rigid three-dimensional objects with textures on them or with colors on them, but actual kind of, blending is the actual proper word and the only way I can describe it. This is stuff that happens in the rasterization as well. There is one thing I'm going to add here though, or at least one thing, depending on the time, and that is the depth test. So can you see how we could implement the depth test into this? Like if we just look at where do we get the original depth value to begin with? Do you remember that? Like in which calculation? Before clipping, projection. The projection matrix is what takes our three-dimensional objects and flattens them out onto a two-dimensional window. So we take our x, y, and z coordinates and we use perspective projection to flatten them out into only x and y coordinates. But what we did with the projection matrix is we kind of used the z coordinate as well to do the pseudo depth. So even though we're not really using that throughout, we calculate the pseudo depth, and actually in clipping it's used in some way. We're not going to go too detailed into that. But the main thing we're going to think about, we're just going to view the depth value, the pseudo depth, like any other varying variable that we linked to our vertex in the vertex shader. So we set values to some varying variables. Through the projection we ended up with clip coordinates, which include x and y values, so those are kind of varying variables as well. But then we have the pseudo depth, which is our z value. And OpenGL actually uses that. So if we have depth test enabled, so if we do GL enabled depth test, that means OpenGL is going to add a little test in here. It's called the depth test. And where it fits in, I'm going to make a little room for it here. So for x in x left, okay, we found y, we found x, and so let's stick it in here and say we are going to find, well actually first we have to do part of this here as well. We have to find left and right value for pseudo depth. Let's just call it for depth. And we can call that z as well. It's kind of, you'll see some sources that talk about the z buffer, some sources talk about the depth buffer. It's the same thing. So here we find left and right values for the pseudo depth. Here we find, let's just say z value. Same linear interpolation. we end up with a z value for this pixel, and this we stick in here, and it adds an if sentence. So if we're doing depth testing, simply say if the z value is less than, let's just call it the z buffer, number x, y, then we actually do the rest. Otherwise, we just skip this entire fragment. Does that make sense? So what we do here is we do all of this, we do all of this, we put things in the frame buffer. Let's see if we can make this a little bit clearer on the other board. You can actually go ahead. I filled all of this in too well. Take this out here, and we can change the bottom part here. We say if our z value here, or our pseudo depth value for this particular pixel, is less than, let's call it z buffer number xy, then we're going to do the rest of these things. Then we're going to find values for varying variables. And then you can start thinking about optimization as well. Run Fragment Shader. Run Fragment Shader. Main. Can actually add that here. Run Fragment Shader main. And in the end say our frame buffer number x, y equals gl underscore frag color. So this would not be c left in this case. We could actually say this is kind of, let's call it v left and v right, and say these are just all our varying variables. You write it up like that, varying, and then we can say for each varying variable. Add these things in. So for each varying variable that we have, we find the left and right value for those, we find the values for here, we run this fragment shader, but we only do this if the depth value is lower than what's already there. What does this mean about initializing the depth buffer? Like if I start rendering a frame, what values do I want to put into the depth buffer? Yeah, so basically the highest possible values depending on the pixel depth of my frame buffer. So if I have an 8-bit depth buffer, that would be 256. If I have a 24-bit depth buffer, that would be 16 million, whatever. I just put the highest value in here, put the max value in them to clean it. What do I have to add here, though? It's not enough for me just to put this. Yeah, so I also have to say the z buffer number xy equals my z value. So this pseudo depth value is closer than whatever was already in the frame buffer. If nothing was in the frame buffer, obviously it's closer. But if we already drew something into this pixel, if something already filled this pixel, then either the new value that we have is closer and then we override it, or the value that's already there is closer, and then we simply don't do any of this. And here we can start thinking about optimization. Like, do we really need to find the left and right values for all of these varying variables if we end up throwing it away? The answer to that is no, we don't. So an optimized version of this would probably make sure that we only calculate as little as we need before the depth test. So we need to calculate x left and x right, and we probably store t left and t right because we don't want to recalculate them if we need them later, okay? So we have x left and x right. and we need left and right values for the depth value. Then we go in here, and we calculate the z value. If it's higher, then we can just skip all the rest. If it's lower, then we have to make sure that we found the left and right values. But we only need to find them once. We don't need to find them for every pixel. We just need to find them once for each scan line. But if none of the pixels in the scan line actually show, we probably want to delay calculating this until at least one of them does. And then you can look at ways to not have to do this in this order, but kind of do it for every pixel. But let's not worry about that. So, questions regarding this. Does this make sense with the depth test? That the depth test is done per pixel. So we calculate pseudo depth. If we look at the pipeline, we calculate pseudo depth per vertex, like all of the other values. But we don't want to just kind of throw away a whole object or not, like take a whole polygon and say it's behind something or it's not behind something. We have to do that per pixel. Because obviously, oops, if I draw another polygon now and it has vertices that are here, here, and here, you know, all of this is going to fill in nicely. But as soon as I'm in a pixel here, I need to make a decision. Is that pixel behind whatever was drawn before, or is it in front? And because we don't store a state about all the objects that have already been sent through the pipeline only holds state for the way it's supposed to render and whatever vertices are being sent through right now. As soon as we finish drawing this polygon, this information is out. We can't compare polygons that are sent through the pipeline. The only thing we have to compare is whatever we put in these buffers. And the fragment shader and these fragment operations, they have access to basically the location in the pixel that we're at right now of the buffers that we're using. So right now we're looking at the frame buffer, which holds the color, and we're looking at the depth buffer. But we can set up other buffers. We can set up stencil buffers and some alternate buffers and things like that if we want to go into complex systems. But more or less, we just have access to these buffers in the XY coordinates that we're working with right now. So in order to know if something's in front of or behind something, we can't go back in time and see what was happening then. Except we can go into the buffer and see what was written in the Z buffer in this particular location. So we can imagine this is the frame buffer, but this is also the Z buffer. So the Z buffer is kind of just another depth to the pixel, just another depth in the resolution of the frame buffer. And then, you know, do we have a frame buffer that's 24 pixels, no, sorry, 24 bits per pixel, meaning that we probably have 8 bits per color of 3 colors. Do we have a 32-bit frame buffer that also has alpha values? Do we have a Z buffer that's 8 bits or 24 bits, so on and so forth? That's kind of the depth. If we imagine like the depth in bytes or in bits of our buffers here. But in general, we can imagine that the slice that we have into all of these buffers is just in this pixel. We can look at the color, we can look at the depth value, we can look at anything that we've already stored about this pixel. And so, in this case, let's imagine that what's already in there, which is from the black triangle here, is actually closer than what we're drawing now. Then we simply stop the rasterization here and just go to the next pixel in this loop. So within this scan line here, for instance, this one is going to be behind, this one's going to be behind, this one's going to be behind, but then suddenly we have a pixel that we show, and so on and so forth. Then we go into the next scan line and we have some of the ones behind, some of the ones in front. So just within this for loop, some of them will fail the depth test, some of them will pass the depth test.
Can you use the Z value in the vertex shader? Like, is it a variable that you can use in the calculations?
Not really. So in the vertex shader, you don't really have the Z value, because the Z value is really part of kind of the last calculation you do, and it's when you send it into OpenGL, you send in clip coordinates that OpenGL understands, and the Z value is kind of, you're already calculating it here. But of course, I mean, you're calculating it, so you have access to it. Is there something in particular that you're thinking?
Yeah, like light absorption, so like light doesn't go like from here to forever, like if it would be like kind of absorbed by air or something.
Yeah.
that
So,
kind of
so like
idea.
attenuation, distance
Yeah.
attenuation on
Yeah.
light or something. You can use that in the vertex shader, and you can use that in the fragment shader. But I don't think this distance value would. Well, I don't think the pseudo depth value would be a good value for that because it's such a weird non-linear function that it's on.
That's true.
But you have, like in here, you're already calculating the v vector, which is the distance from the object to the, no, not the distance, which is the vector, the direction from the object to the camera, because you're using it in your specularity.
Yeah.
So let's say you take the length, no, wait, not that one, the one that's used in diffuse, S vector, which is basically the vector from the object to the light. So I guess you could take the length of that vector and then you have something that you can use. So imagine the distance from the object to the light would be more interesting in this case than that. Yeah, when we start looking at fog as well, we can start looking at ways to optimize these things, kind of decide which distance we use, or if we use some simplifications of these distances. But, and obviously, while you're in the vertex shader, you don't have kind of access to the buffers because you're not in pixel space yet, so that doesn't help either. So it's my feeling kind of that the pseudo depth value is not something that you can use a lot in your calculation because the function that it's on is so nonlinear and strange. Where we're at here. Are there questions regarding this? I'm just wondering if there's anything particular that would be interesting to add into the rasterization algorithm at this point. So we have the depth value. If we want to complicate this a little bit, obviously this if sentence would only be if the z value is less than this. But if depth testing is actually being employed and the z value is less than this, otherwise, you know, if it's not being employed at all, we just override anything. So yeah, just the understanding that the pseudo depth value is calculated in the vertex shader per vertex. Those values are then linearly interpolated like any other values until we kind of have them in pixel space. So we have a pseudo depth value in the end, or z value for every pixel, and the depth test is done in rasterization for every pixel. So in OpenGL, you do something that's called GL enable GL depth test. And the reason this is called depth test is because this is just a pass-fail test for every pixel. Like, am I going to do this pass-fail test for every pixel? That is, if I fail it, I don't draw this fragment, I don't run the fragment shader, I don't calculate all the varying variables, I just continue. Or do I pass it and I do all of those things? So the depth test doesn't only make sure that things are drawn in front that are supposed to be in front, it also saves us a lot of time on running the fragment shader and doing all of these things for pixels that aren't drawn. So there's actually an optimization possibility in here, which is if you have a way to draw your scene or draw whatever's left after you kind of throw away things that you definitely can't see and things like that. But you can't completely be sure what's going to be drawn behind something else, or some objects are partially behind something, so you have to draw the entire things. But you can order them in a way that you draw the closest things first and the things that are furthest away last. That means you get more failed depth tests, and that means you get a faster rendering. Does that make sense? So if I draw something that's really close to me, then I draw things that are behind it. A lot of these things will fail the depth test, and then I won't even draw them. If I start with the things behind me, OpenGL will actually render them in full light, even with transparency, with all the stuff that you render them with, and then it'll just draw something else on top. And you've wasted all the time on running the fragment shader and setting these things up per pixel for pixels that will then just be overridden. So if you manage to order your objects from closest to furthest away, or even within the objects, if you manage to order the polygons from closest to furthest away, you can actually get a fairly big optimization in the running time of your rendering, because more depth tests are failed, and thus fewer pixels are actually rendered, and the fragment shader is run fewer times. So we're only running the fragment shader for something that will actually be seen, and not running the fragment shader for things that will later be obscured. If there are no particular questions, I think kind of this base rasterization idea is covered here. The way to fill in the actual pixels that are covered by a polygon. We'll look at transparency and fragment operations later, but if we look at the OpenGL pipeline again, we can also say that we've kind of closed the OpenGL pipeline. If we go ahead and implement these things, we could actually implement a pipeline now that ends up drawing into pixel space and filling in polygons into an image, and storing that into a bitmap image or rendering it on screen. So the geometrical transformations here in the vertex shader, plus lighting calculations, plus taking these values through clipping through window to viewport, and taking these values and actually finding pixel values for them, running the main function in the fragment shader, and displaying the correct color in the correct pixel for all the pixels that a polygon fills, is something that we've kind of covered the basics of throughout the entire pipeline. So I'm going to claim that we've kind of closed the pipeline at this point. From now on, we're going to look at texturing, we're going to look at fragment operations, we're going to look at blending, but the overall geometrical and lighting calculations that actually put a three-dimensional image on the screen, they're kind of covered at this point. So questions? Or just have a nice weekend.